So we'll discuss noise mechanisms in photoreceivers that we started last time, right? So we saw that there are two main noise mechanisms. One is short noise, one is thermal noise. And we saw that typically the pin photoreceivers, they operate sort of in the thermal noise limit, where the thermal noise dominates over the short noise, right? So if you keep increasing, yeah, sorry.
Sir, could you please give us that quiz one and minor, average, and highest marks, sir?
I mean, I think you can see that on the Moodle already, right? It gives you, it certainly gives you average. I don't know. Sure, I can. I mean, average. I think you can see on Moodle.
Okay, okay, sir. And also the
If not,
highest marks, sir.
okay, I'll send an email with all average, highest, standard deviation. Right. So now, if you keep increasing the power, right? What happens is at some point, so we know that short noise scales with the photocurrent or the input optical power, right? So the short noise keeps increasing, but whereas the thermal noise we saw is constant, right? It only depends on the operating temperature and the load resistance, right? So at some point beyond a certain input power, now the short noise will take over. Okay, so basically for very high optical powers, typically for pin photodetectors, like you have to cross like tens of milliwatts, maybe close to 100 milliwatts to go into the short noise limit. Okay, typically up to a few milliwatts of power, which is sort of typical for optical communication links, you are in the thermal noise. Okay, so here we mean that the variance of the short noise current is much higher than the variance of the thermal noise current. Right, so if we look at that expression of SNR that we had, so if we neglect the thermal noise current, maybe I'll write that complete expression first. Right, so the numerator we had the photocurrent squared, which is basically responsivity times the optical power squared, and the denominator had two terms. First one was the short noise. It went as the photocurrent. Right, so let's. So we also had a dark current, but typically for high optical powers, this average photocurrent is much higher than the dark current. So let's neglect the dark current. Right, and then we had the thermal noise term, which was like this. Right, so basically the short noise limit, we are saying that this is much smaller than this. Okay, so if we do that, so you can see that one power of this cancels out. Right, so you just get responsivity times optical power divided by this constant electronic charge times the bandwidth. Okay, so recall in the thermal noise limit, the SNR scaled as the square of the optical power, right? So this thermal noise term was constant. So when we neglect this, the SNR scaled as the square of the optical power, right? So again, this is the electrical SNR, right? So this is proportional to the square of I square R. But in the short noise limit, we can see that this electrical SNR scales linearly with the optical power. Okay, so and you know that we have this expression for the responsivity in terms of the quantum efficiency of the photodetector, right? H nu is the photon energy, use the electronic charge. So if we use this expression for the responsivity here, we can write this in terms of the quantum efficiency of the detector. Okay, so basically it's scaling as linearly with the optical power and inversely with the bandwidth. Okay, so we can even write this sort of or simplify this expression further if we write it in terms of the number of photons per bit. Okay, so let's say we have optical pulses we are detecting, right, of duration TB, which is 1 over the bit rate, right? And so let's say that the optical power here is the P optical power here, right? So bit 0 we are not detecting anything. So so if you look at the energy in this pulse, right, that is P optical times the bit period, right, or equivalently P optical divided by the bit rate, and the energy in this pulse is basically equal to the number of photons in this pulse times the photon energy. Right? So this is the energy per bit or per pulse, and this is the number of photons per bit, right? So we can substitute for the optical power in terms of the number of photons per bit here, right? So if we substitute that here, you can see that these factors of the photon energy will cancel out, and so this this detector bandwidth here, delta F, right? Right. So we typically saw that. So if you look at some 3 dB bandwidth here, right? So for example, in the last class we had discussed this linear channel filtering, right? So we saw that we had some filter like this, which went to 0 at the bit rate. So one typical delta F number that we can take is sort of like half the bit rate. Okay, so delta F is like something like the 3 dB bandwidth of the detector. We can sort of roughly assume it to be half the bit rate. Of course, it will depend on the exact circuit that you are using for the photo receiver, etc. But just as a to estimate this sort of order of magnitude. Okay, so if you also put this delta F equal to P over 2, so that factor of the bit rate will also cancel out, and you'll be left with basically just the quantum efficiency times the photons per bit. Okay. So you can see that in the short noise limit, basically your SNR is just scaling with how many photons you have in your bit. Okay. So this eta typically we saw is around, let's say 80-90% for the photo detectors, like in-gas photo detectors that we use, right? So basically it's scaling with the number of photons. Okay. So for example, if I want an SNR of 20 dB, then basically I need something like 100 photons, right, per bit. So if we assume a wavelength of 1.55 micron and a bit rate of, let's say, 10 gigabit per second. Okay, so from here we can calculate what optical power that corresponds to. Okay, so that corresponds to about 130 nanovolts. Okay, so you can see that's quite a low optical power, right? So of course, this is assuming we've neglected thermal noise, right? So if you were limited by short noise, then we could get SNR of 20 dB, which is pretty high, right? With as low an optical power of like hundreds of nanovolts. So, whereas if you compare it with the expression we had for the thermal noise, right? So this is the short noise limit. If you compare it, if you were in the thermal noise limit, which is typically the case in practice. So there, if you want an SNR 20 dB, typically the optical power required is more than a microwatt, few microwatts. Or if you look at the number of photons per bit, that is more than 1,000 photons per bit. Okay, so this is, so you can see that basically we're operating with, so this, recall this discussion about Poisson distribution we were having, and then approximating it with the Gaussian distribution. So this is basically the average number of photons we are detecting per bit, right? So you can see that this number is much bigger than 1. So this Gaussian approximation works. Specifically for the short noise. I mean, thermal noise is pretty much Gaussian. But yeah, so for typical pin photo receivers, we are typically in this limit. Okay, unless in certain cases, for example, if you use so the thermal noise, recall this was proportional, inversely proportional to the load resistance. So if you use some very high load resistance to have very high gain, for example, that would limit your bandwidth of operation, of course. Right? In that, when you use very large arrays, let's say I don't know, tens or hundreds of kilo ohms, then the thermal noise goes down, right? And then you might be in the short term for high value growth. But then, yeah, that limits your bandwidth of operation. Okay, so that's sort of the level of noise we have for pin photo receivers. Now let's discuss for APDs. Right, so for APDs we saw that the gain, the responsivity is enhanced by factor m, right, where m is sort of the avalanche multiplication factor, or the gain we get due to impact ionization, gain in photocurrent. Right, so you can imagine that for the same optical power now with APDs we will get a higher photocurrent, which means that the short noise will also be high, right, because the short noise scales with the photo. So just as pin photodiodes typically work in thermal noise limit, when we use APDs, typically they will work in the short noise limit for typical powers again, let's say. Okay, so again, so recall the photocurrent for APD receivers was multiplied by this factor m, and this R is the usual responsivity that you have for a, let's say, a pin photodiode. Okay, so and we saw basically the SNR, electrical SNR is proportional to the square of the photocurrent. So we can see that, so naively you would expect an enhancement of m square, right? So that would be true if, for example, we were still in the thermal noise limit, right? So in the denominator here we have the short noise plus thermal noise. So if you were in the thermal noise limit, that is independent of the photocurrent, right? So if you were still in the thermal noise limit, then the SNR will go up by a factor of n square, right? And we saw that typical values of m for the APD is like maybe 10 to 40 in that range. So you can see that the SNR will go up by a factor of 100 or more, right? But again, the point is that because the photocurrent is going up, the short noise is not negligible anymore. So the enhancement in SNR is not as good as we would expect. Okay, so the thermal noise is the same as for the pin photodiodes, because yeah, that doesn't depend on any that doesn't depend on photocurrent. If you look at the short noise, okay, for APDs that actually scales like this. Okay. So you can see that it's quite bad actually. So the short noise also has a factor of m square. Okay. So you can think of something like, so the fluctuations are also getting enhanced by a factor of m. Okay. So which means that the variance or mean of is square gets enhanced by n square. Okay. And not only that, there's an extra factor here, Fa, okay, which is known as the excess noise factor for an APD. Okay. So just from this avalanche multiplication gain, you would expect that the short noise should go up by a factor of n square, because the current is getting enhanced by a factor of m, right? So the short noise current fluctuation will also get enhanced by m. So I square will get enhanced by m square. So that's what you would expect just from the gain. But on top of that, the noise is actually more than that, by this excess noise factor, where this excess noise factor is also a function of the gain. Okay. It goes like that, where Ka prime is this ratio of the hole to electron incarnation factors, which is just Ka, this factor Ka, remember that we had defined to calculate this n, right? This n depended on this Ka. So if alpha is less than alpha e, and it's equal to alpha e over alpha h, which is the inverse of Ka, if is the other way. Okay, we typically saw that typical detectors are working in this, where alpha is more than alpha h, right? Or Ka is less than. So for the typical detectors that we use, especially for telecom, it will be using the top row. Okay, so you can see that this Ka prime is some number between 0 and 1, right? Because so if this is true, then this is already less than 1. But if it's the other case, then you take the inverse, which is also less than 1, right? So Ka prime is between 0 and 1 such that Ka prime and 1 minus Ka prime are between 0 and 1. So we can take a look at how this excess noise factor scales with the APD gain. Right, so naively you would have thought that the larger gain I have, the better it is, the higher SNR I'll get. Okay, but from here we can see that as you increase gain, actually your noise starts increasing, especially once you start going into the short noise limit. The noise starts increasing at a faster rate than the signal. Okay, so then your SNR will actually start worsening with increasing gain. Can we justify why we are not neglecting dark current? I mean, in most cases, we would still neglect dark current here if the optical powers are reasonable enough, but we just keep it because so for the APD again, so what you're saying is right. So M is large, right? So that means that we could be in the short noise limit for lower optical powers, right? For the pin photodiode to get into the short noise limit, our optical power had to exceed a certain value such that it became larger than the thermal noise, right? So we are at large optical powers where the dark current is low, but for APDs, we might already be in the short noise limit for low powers where dark current is not may not be negligible. Okay, but just let's look at this excess noise factor. So this FA versus APD gain M. Okay, so both the x and y axis is sort of in log scale. That's why I didn't say that. Okay, so now basically we're plotting this curve for different values of Ka. Okay, so Ka equal to 1 would mean we have only this term goes away, right? And so that we just get M. So we get a straight line. Okay, so this is for Ka equal to 1. Now as we decrease Ka towards more the actual values that we see, this sort of goes down. Okay, so this is Ka equal to 0.5, right? So we saw that for the in-gas photodetectors that we use, typically we are around this value of Ka. 0.2, 0.05, and then the other limit Ka equal to 0. Basically, if Ka is 0, now you only have the second term, which is 2 minus 1 over M, and then for large M that saturates to 2. Right, so that's why this is like saturating to 2. Okay, so you can see actually you want as low a value of Ka as possible because your noise is lower, right? So this is a factor by which the short noise is getting enhanced. And best you can do is if this is equal to 2 at Ka equal to 0, right? And as you increase Ka, the noise keeps increasing. The worst case scenario is Ka equal to 1. So recall when we were discussing this gain factor M, right? So that also depended on Ka, recall. And for this situation, Ka equal to 1, we could actually get to a point where M sort of was shooting up to infinity, right? And we said that typically we don't go to that regime because the noise also shoots up. So, and you can see that explicitly here. Okay, so K equal to 1, the noise also much worse. But so typically we are somewhere in this regime for typical devices that we use. Okay, and the gain values are somewhere here that we use. So you can see that the excess noise factors are typically like about, let's say, 5 to 10 in that range. Okay, so we enhance the noise by order of magnitude higher than what we would just expect from the gain. So, okay, so basically, to summarize, so if you operate the APD at very low optical powers, right, such that you are still in the thermal noise limit, right? So this term is still lower than this. Then basically the SNR that you get with the APD is enhanced by a factor of m squared with respect to the SNR that you get from the pin photo detector, right? So that's the best case scenario, but that only works till very, very low optical powers. Okay, maybe like below a microwatt or so. But once you go up to these reasonable optical powers, you go into what into the short noise limit with APDs, right? And in the short noise limit, so we can take this expression here, right? Again, if you neglect the dark current, right? For a moment, let's neglect the dark current and use this expression in the SNR. So here we get m squared times responsivity optical power squared, and in the denominator we'll have this 2 cube m squared Fa, and responsivity times optical power times the bandwidth. Okay, so m squared gets cancelled out. Okay, so here we get, and again, if we substitute step by step. So I get okay. So you can see that. So for the pin photodiode, this was so this factor of Fa was not there, right? If you look at the SNR for the pin photodiode in the short noise limit, we got Rp divided by 2Q delta F. We didn't have this Fa. So now we can see that with APD, actually the SNR in the short noise limit is actually worse by a factor of Fa, right? Which typically can be, let's say, around 10, right? So if we write in terms of like the photon number per bit, like we did for the pin, so we get down the photon number divided by this excess noise factor FA. Okay, so you can see that this is worse compared to the pin photodiode by this excess noise factor. Okay, so if you still remain in the thermal noise limit, your SNR goes up by a lot by using an APD. But if your powers are such that you go into the short noise limit, your SNR actually worsens by factor F. Okay, and typically when we use APDs, we are sort of going into this regime. Okay, basically we can afford a little bit reduction in SNR in exchange for getting a higher signal. Okay, so for telecom applications, typically that's where we use APD. Like we can afford a slight reduction in the SNR for slightly higher signal. Basically, we want more current or more voltage for the electronic circuits at the back end after the receiver. In that case, but if the light level is so low that you still remain in thermal noise limit, then you get a great enhancement in the SNR. Lower limit of FA equal to 2. Yeah, so the best FA can be is 2, right? That is if your K is close to 0. Typically, for the in-gas photodiodes we use, K is somewhere around 0.5, so, and the gain values are somewhere here between 10 and 50, so FA is around 10 for typical in-gas detectors. But yeah, the best you can do is 2. You cannot be if you look at typical gains above 10, then 2 is the best you can do for this excess noise factor. Okay, so we can see that, so what is happening, right? So initially for very low optical powers, or when the photocurrents are low, right, the SNR is going up with increasing gain, right? And then at some point, so let's look at it this way. Let's keep our optical power the same, okay? And just keep increasing this gain m. See what happens, right? So initially, for small m, we'll get this enhancement because, so for m equal to 1, we start from the pin photodiode. We are in the thermal noise limit, right? And as we increase m slowly, we still remain in the thermal noise limit for some time, and we get this enhancement m square. Right? Then as we keep increasing, we introduce more and more short noise, right? So this SNR enhancement starts going down, right? At some point, SNR reaches a maximum, and then once, if we keep increasing m further, then we go into the short noise limit, and then the SNR actually, you can see, starts going down. Okay, so in other words, if I plot SNR for the APD versus gain factor m for a given optical power, okay, P optical equal to some constant value, and we just change m and see how the SNR is scaling. So SNR will go up, okay. So if I start from m equal to 1, which is the pin photodiode case, so initially SNR will increase and then it will start dropping and then it will go below where I started. Okay, so there is an optimum gain here, right? So for a given optical power, there is an optimum gain which will give me the maximum SNR. Okay, so if I have an optical communication link and I know how much power is being sent at the transmitter, I budget for all the losses along the link, then basically I know what optical power I will get at my photodetector at the receiver, right? So if I know this, then I can use a detector with this optimum gain to get the maximum SNR and consequently like the lowest bit error rate. Okay, so we can calculate what this SNR is from this expression for SNR we have, right? So we take the whole expression now. So this will be so here you are in the thermal noise limit, here you are in the short noise limit. For this optimum gain case, you will be somewhere where both noises are sort of equally important. Okay, so you take the entire expression then, right? So basically you take SNR, so m square r square p of square divided by this plus this. Okay, so you can see that now this is some complicated function of f, m. You have a m in the numerator and you also have m, and this is also a function of m, fa. So you have a function of m in the denominator, you have a function of m in the numerator. So basically what you can do is differentiate this expression, put it equal to 0 to find the maximum. Okay, so if you do that, so you get this equation for the optimum gain. Okay, so you get a cubic equation in M, where all others are constants, right? K, we know temperature, noise factor, the amplifier circuit, load resistance, optical power, responsive theta. So the solution of this will give me what optimum value of M that I need in my APD to maximize this. Okay, and typically so if you look at right, so what this is telling you is there is an optimum gain, right? Given the link you have and the power that you expect to receive, there is an optimum gain that you want. It's not that higher gain is always better. Right? That's what this is telling you. So if we plot, for example, this optimum gain of the APD versus the received optical power dBm. Okay, so minus 20 dBm is 10 microwatt. Minus 30 dBm is 1 microwatt. Minus 40 dBm is 100 nanowatts. Okay, so you can see what range of powers we are talking about for APDs. It's sort of in the 100 nanowatt to 10 microwatt range. Beyond that, we prefer to use pin phototypes because the optical power is high enough that you can get a decent signal from it. So now, again, so this depends on this value of Ka. Okay, so when k is close to 1, 1 minus k is close to 0. Okay, which means this term is small compared to the first term, right? And then you can see that, so if I neglect this term, then the optimum gain m will be the cube root of this factor here. And here I have optical power in the denominator. Okay, so in that case, when k is close to 1, the optimum gain will scale as P optical to the minus 1/3, right, or cube root of 1 over the optical power. In the other case, when k is close to 0, then this term is small, and I have this term. In that case, you can see m scales just inversely with the optical power. Okay, so k equal to 0 will be here somewhere. This is k equal to 0, and so here m optimum is proportional to 1 over p optical. Okay, so the slope is so minus 1. As I increase Ka now, the optimum gain goes down. So, okay, and also the slope. The slope is also going down. Okay, so this is the other limiting case, k equal to 1, and here m opt is proportional to 1 over the cube root of the optical. Okay, so you're increasing Ka from here to here. So it's like 0.21, 0.1, 0.5. Okay, so silicon APDs, which are used for visible wavelength range, the Ka is around 0.1. Okay, so you can see that the optimum gain value is around 100. It changes a little bit, but it's around 100 depending on the optical power. But the optimum gain is around 100. So this is where sort of silicon APDs operate. In-gas APDs are somewhere here. Okay, so there the optimum gain you can see is like 10 to 50 in that range. Okay, so basically, yeah, for these in-gas APDs that we use for our telecom links, basically we want to keep the gain around in this range of 10 to between 10 and 40 or something to maximize the SNR, right? We don't want larger gain than that because the SNR actually starts dropping. Okay, I hope that's clear. Any questions? right? And basically we saw that in terms of the device design, the way to control this M is by the thickness of that extra P layer that we add, which acts as the avalanche multiplication layer. By controlling that thickness, you can control this M. Because all other like Ka and the electron and hole impact annihilation factors, all that is a constant once you choose your material. Okay, so now we see basically how the SNR, or we have seen how the SNR is varying in different regimes of operation, whether you're using a pin photodiode or a APD, and depending on the optical power, whether you are in the thermal noise limit or the short noise limit or somewhere in between. So how does this? So now let's see finally, for example, how we characterize a link. A communication link is the performance. The metric that we use is the bit error rate, right? That's what finally we are interested in. And so you might have heard, so for example, typically we want like a bit error rate less than 10 to the minus 9, right? Which means 1 out of a billion bits are in error, right? So how does this SNR translate to the bit error rate? So let's briefly see how that how the SNR translates to the BER performance on the link. Right. So now let's imagine we are getting this bit stream, right? Optical power. So for now, let's assume simple O on-off keying modulation, intensity modulation, and then direct detection using a photodiode. So the photocurrent that we'll get will have pulses, right, corresponding to bit 1 and 0, but it will also have noise, right? So if we only assume let's say for now, the only noise mechanisms we are looking at are from the receiver itself. So we have short noise and thermal noise, but so basically they add up to my signal, right? So now instead of just seeing smooth pulses, now I have this noise sort of imprinted on the photocurrent, right? So this is the photocurrent as a function of time. So this is some bit period here, TB, right? So this is showing you, for example, a bit 0, bit 1, and bit 0. Okay, so we saw that we use various circuits after the photo detection to sort of reduce this noise, filter out the noise from the signal, do some post processing, and then finally send it to a decision circuit, right? So basically what we do is we have some threshold level here, right? So which we call the threshold current ID or detection threshold ID. Okay, so if you average this over many bits, there's an average current for bit 1 here, okay, which we denote by I1. And then there's an average current for bit 0 here, which we can denote by I0. Okay, and then there is, of course, noise, right? So for example, let's say I'm sampling the value here in at this time instant sometimes I will get this, which is higher than I1. Sometimes I will get something below I1, right? So every time I sample, I'm getting a spread of values around I1. If I take the average, I will get I1. But there is a spread. So if you again model, if you plot the frequency or if you plot the distribution of the values you get, you'll get close to a Gaussian distribution. Okay, so most of the times you will get something close to I1, right? And the deviation from I1 either up or down will go down. The probability will go down as you go away from I1 more and more. Okay, so if you plot the statistics of the samples that you get, you'll get like a Gaussian kind of distribution. Okay, where so the standard deviation you can denote by sigma 1. Okay, for bit 1. Similarly, for bit 0, I'll get a spread of values, and I can, if I plot the distribution, I'll get something like a Gaussian distribution with again standard deviation sigma 0. Okay. So now, basically, my decision circuit, what it does is so it's now sampling the value, and if the value it gets is above this threshold value that we kept ID, then we say okay, the received bit is 1. If the current that we get is below ID, we say okay, the received bit is 0. Okay, so you can see how you can get an error. So let's say there's a noise fluctuation here, right, which is big enough so that when you sample here, although bit 1 was sent, but at the receiver, the value that you got was below this ID. Okay, so you can see the probability of that will be how much of this distribution, the tail of this distribution going below ID, right? So I1 has this Gaussian distribution centered at I1, right? So basically it's going down to infinity, plus minus infinity to either side. So there's a small tail here which goes below ID. Okay, so this is the area under this curve below ID here. Is the probability that you can get a sample here which actually is below ID, although you have bit 1. Okay, similarly for 0, right? So this Gaussian distribution, the tail of it going above ID, right? So that is the probability that you have a noise fluctuation here, such that you get a value above ID, although bit 0 is. Okay. So the bit error rate that I will have will be, so the probability that symbol 1 was sent at the transmitter multiplied by the probability that I detect 0 at the receiver, right? That's one kind of error, that 1 was sent and 0 was detected, right? So this would be probability that I detect 0 given 1 was sent, right? And the other contribution will be if 0 was sent at the transmitter and I detect 1 given 0 is sent, right? So that's my bit error rate, right? This is the probability that 1 is sent and 0 is detected. This is the probability 0 is sent and 1 is detected. Okay, typically if I look at a very long sequence of bits, I'll have equal probabilities of 0 and 1. So typically for a very long sequence of bits, this will be half. This will also be half. So basically the bit error rate will be the average of this probability that I get, that I detect 0 given 1%, and the probability that I detect 1 given 0%. Right, which also makes sense. Okay, that's what you would expect the error to be. Okay, so now, so how do we model this, right? So basically, you can see, we can calculate the bit error rate by these probabilities. And what are these probabilities? That's just the area. So this is the probability distribution function. And the probability of this error, right? So probability 0 given 1 was sent. So if 1 was sent, then I have this probability distribution for the photocurrent. And the probability to detect 0 is if this, what is the area of this distribution below ID, right? So this probability 0 given 1 is basically the area of this portion of the curve. Similarly, probability that I detect 1 given 0 was sent is the area of this curve for bit 0 now above ID. So just now a matter of computing these integrals, which is a probability, right? Okay, and so from here you can straight away see that basically the noise is assumed to be Gaussian, right? So for thermal noise, it's true, like it's Gaussian noise. And for short noise, we saw that if the number of electrons, average number of electrons per unit time is large, much bigger than 1, then it is also pretty close to a Gaussian. Okay, so in practical cases, this is quite well modeled by Gaussian. But in general, you could imagine maybe for some other kind of optical communication system or some other communication system with other sources of noise, this could in principle be different, this distribution of the noise. Right? But the idea would be the same. Just if you know the probability distribution of the noise, then basically you find the bit error rate by evaluating this integral for the error. Okay, so yeah. So now this standard deviation, right? That's, or basically the variance is sigma square. That is basically the variance of the noise currents that we studied, right? For the short noise or thermal noise. So basically, the sigma 1 or 0 square, the variance, is basically the contribution from short noise. So short noise would depend on right, whether you have bit 1 or 0, because that depends on the current level, plus thermal noise, which is independent of the current, so it does not depend on which bit. Okay, so yeah, so now assuming the noise to be Gaussian, then P0 given 1, you can evaluate with this. Right, so 0 given 1 is the area under the Gaussian curve here below ID. Okay, so basically we are integrating from minus infinity up to ID. Of course, you can say that the actual photocurrent that I get won't be negative, right? It can't go below 0, but basically what we are also assuming that this is sufficiently above 0 such that so the tail of this distribution going below 0 is negligible in any case. So whether you integrate from 0 to ID or minus infinity to ID, it's not, the difference is negligible. And integrating from minus infinity to ID is easier because we have standard relations for Gaussian functions for that. Okay, but so this minus infinity is technically speaking an approximation, right? This should be start from 0, but the error is small enough if this ID is sufficiently above 0, or in other words, if the sigma 1 and sigma 0 are much smaller than ID, right? So that this tail has, this distribution has come down basically to 0 by the time it crosses. Okay, so I have a Gaussian function here with mean I1, right? Variance sigma 1 square. I is the variable of integration. Okay, and this is just a normalization factor such that if I do this integral from minus infinity to infinity, I'll get 1. Okay, so I hope this is clear, straightforward. So this integral for a Gaussian function from like 1 and so minus infinity to some number is well known. So it's known as an error function or complementary error function. So this is just ERFC. So this is known as complementary error function. Okay, so you can see that it's known by the name of error function. So this shows up in many places. This integral of Gaussian from either minus infinity to some value or some value to infinity. So the other way around, some value to infinity is known as the error function. Minus infinity to some value is known as the complementary error. So you can see that basically this is showing up in many places to compute the error in many systems. So here also it's showing up when we are trying to calculate bit error rate. So complementary error functions. Okay, so this complementary error function is defined like this. So for an argument x, it's basically, okay, so it's actually defined like this. So it's the integral from x to infinity of e to the minus y square dy. Okay, so basically, so it's like a normalized Gaussian function here, right, with sort of standard deviation 1. And it's the area under the curve from some value x to infinity, right? So this area here is basically the complementary error, right? So you can see we have something similar here. So minus infinity to some that we can, so if you want to convert it to this form, you can first do a change of variables, change from I to some minus I, so that now this integral goes from something to infinity. And then you have to normalize such that you get this form, right? So you have to do a change of variables. Anyway, so you do that, you will get this. You can check. So there's a question, why is it called bit error rate? It's just the probability of making a false decision, yes. More precisely, maybe it should be called the probability of error rather than bit error. I mean, it's not a rate in the sense that it's not like, it's not a rate in time, right? It's not like the bit rate or something. But you can think of it as a rate in the number of samples, right? So if my BER is 10 to the minus 9, that means every 10 to the 9 or every billion samples, I'll get one error. So it's the rate of errors I'm getting as I'm sampling more and more. You can think of it as a rate in sampling, I guess. But it's not like a bit rate or some rate in time like that. Yeah, it's not. Yeah, you can see here it's more like a probability of error. But this is the technical term which is used. Okay, and then the other P1 given 0 is very similar, right? So try to write it smaller, maybe here. P1 given 0. So now I'm computing this area. So I go from ID to infinity. And now I have a Gaussian with mean I 0 and variance sigma naught square. Okay, so this you can see now is directly sort of in the complementary error function form. Okay, so yeah, so for this you get the complementary error function of ID minus I0 divided by square root of 2 sigma 0. Okay. Or half of that. Okay, so now basically we just add these two up and then multiply by half to get the bit error rate. So I just plug those results here. Okay, so I can take this half out, make this 1 by 4. Okay, so that's the expression for the BER that I have now in terms of actual things that I can measure at the receiver, right? So I1 is the mean current that I get for bit 1, I0 is the mean current that I get for bit 0, sigma 1 and sigma 0 are the variance which I can, again, so basically if I measure a bunch of samples, like you do for example when you make this eye diagram, right? You overlap any of these things, so, right? So you can now see basically this eye here. If the signal to noise is large, then the eye will be more open, and you can set a nice threshold, and you can get low errors basically. Right. So you can see that the error now depends on how far away your mean current for bit 1 and so let's say so this term corresponds to how far your bit 1 current is from the threshold divided by the noise. Right. So how many standard deviations your threshold is away from the mean. Right. Similarly for this case, how many standard deviations your threshold is away from the mean. So the higher that value, the lower your error. Right. So you can see this error function. So as you increase x is basically this. Right. So the difference between your threshold and the mean current that you detect, this probability falls really fast. So if you plot error function, complementary error function of x versus x, it really falls very fast. Okay, so and the other parameter here is this detection threshold ID, right, which we can choose. So depending on different choices of ID, you can see that the BER is varying, right? So basically, I have to choose this ID optimally. So for a given I1, I0, sigma 1, sigma 0, what ID should I choose to minimize the BER, right? So that's something that I should know, right? So that I can set the optimum value of the threshold. Okay, so for that, basically, I just differentiate the BER expression with respect to the ID should be equal to 0. So basically, we'll get okay, so check that. Start from here and then check that you get this. So typically this value here, so it's a log of the standard deviation for bit 1 divided by bit 0. Okay, so this value is typically small compared to the difference of the threshold with the mean, right? So this is like a ratio of the standard deviations to here, and then we take the log, right? So that's, you can imagine, will be a small number. So otherwise, this is a very, it's like a nonlinear equation to solve. But in most cases, we can just neglect this term, right? And then basically we say that the optimum value of ID is given by the solution to this equation. Okay. And so you can see if you solve this equation, the optimum value of ID is just okay. So yeah, so I1 is just responsivity times the average power that I get for bit 1. I0 is some low value, like if for example for OK we are not sending any power for bit 0, then I0 will just be, for example, the dark current or something. Right, sigma naught will be just the thermal noise for bit 0. For sigma 1 it will be thermal noise plus short noise. Okay, so you can see that the optimum detection threshold is a weighted average of I1 and I0, weighted by the noise levels in bit 1 and bit 0. Okay, and this value of how far my threshold is from the average values, this thing is known as Q divided by the standard deviation. Okay, so basically you can see here I can write the BER in terms of Q. Right, so the optimum or the minimum BER that I get for this optimum value of the threshold that I set I can just write as So these two terms are now equal, right? So this is equal to this under this approximation. So then these two terms are equal, you can see. This is just q by root 2, this is also q by root 2. So this just becomes q by root 2. Okay, where q is this? So if you can also plug this expression for the optimum value of the threshold into here to get the q in terms of just I1 and I0 and sigma 1 and sigma 0, you see it's this. Right? So it's something like, so I1 minus I0 is like your signal level, right? The difference in the currents between bit 1 and 0. So that's something like the signal level. And sigma 0 plus sigma 1 is sort of like the total noise level. Right? So there's something like signal to noise ratio you can see. So signal to noise ratio is defined as sort of the signal power divided by the noise power, right? So signal power goes as I square because we're looking at electrical power, right? So so the SNR is something like I square by sigma square. So you can see Q is something like the square root of the SNR. And so you can see that the bit error rate depends on the SNR like that. Okay, so we can look at typical limits here. So typically, let's say if you're using a twin photodiode and you're working in the thermal noise limit, basically what that is saying is that the short noise is less than the thermal noise. So for bit 0 and bit 1, both you only have thermal noise. Okay, so let's say you're using a pin detector in thermal noise limit. Okay, so this is typically the case. Let's say your detected optical powers are in the tens of microwatts to hundreds of microwatts range. Okay, and you're using a pin detector. Then you're in the thermal noise limit, and so basically what that means is that sigma 0 is same as sigma 1, right? Is basically the thermal noise, correct? Okay, so in that case, you can see here that the optimum detection threshold is just the average of I0 and I1. Right, so that's what you would naively expect. If you have equal noise on both bit 0 and bit 1, you just set the thresholds in the middle of I1 and I0. That's the best. Okay, so again, so from this expression, we saw that the error function with the argument, right, this complementary error function falls drastically. So if you plot the BER versus Q, then you get a curve like this. Okay, so we are here in the log scale. So this 10 to the minus 12. We're drawing bigger. Okay, so if you look at 10 to the minus 9 BER, which is sort of like a standard figure of merit that people keep for these fiber links, then that corresponds to roughly Q about 6. Okay, so yeah, so for BER less than 10 to the minus 9, you want Q above 6, right? And Q recall is this, right? So you want sort of like the difference in the currents here to be 6 times the total noise level. And for large values of Q, like beyond, let's say 3 or so, there's also a simpler way to evaluate. I mean, to get exact values for this complementary error function, you have to see a lookup table where basically all these integrals are evaluated numerically and the values have been noted down. But there is an analytical expression that you can easily solve or compute for which works for large values of Q. For largish slice, for Q greater than 3, it works quite well. So e to the minus Q square by 2 divided by Q times square root of 2 pi. Okay, so stop here. Okay, so basically this is telling you the dependence of the BER on the SNR, right? So it's some exponential or Gaussian-like dependence because we said that Q is, or exponential dependence, we said Q is something like square root of the SNR. So Q square is something like the SNR, right? So you can see that the BER is falling exponentially with increasing SNR. Okay, any questions? So this thing that we discussed is quite general. You might have seen this before in like some other like digital communications or anything, right? Because basically we're receiving 2 levels and we model the noise almost something like additive by Gaussian noise, which you have, which you typically take for example, for most kind of communication channels. But note here that the noise may not be additive because if you include short noise, then for example, sigma 1 would depend on I1. So in that case, it's going to be purely additive noise. But otherwise, this computation of, you might have seen this expression of complementary error function and these things before, or other kind of communication systems also.